Wow, super neat. Now say you had a mixture of 3 compounds. How in the world would you separate those? Well, it really depends on what kind of compounds we're using and what their physical properties are. Like, what about adamantine, glycine, and octanoic acid? Piece of cake. So first off, we're going to want to find the chemical properties of these compounds, but lucky for you guys, I have it written right here behind me. Now the way we're going to attack this problem is by looking at the solubilities of each compound in the mixture. Would you look at that? Adamantine is insoluble in water. We can use this to our advantage by doing a recrystallization. But I'm going to need a volunteer to come help explain this process. Do I have any takers?
Oh, so lame.
Yeah, me.
She better not freaking pick me. Ugh.
Yeah, you.
Here we have our flask, our filter, our water, jello, sugar, and almonds. We're gonna mix all 3 of those into our water, making an aqueous solution. After, we're going to pour it through our filter, and then we will see that the almonds are left over because they are insoluble in water.
So now that we are done our recrystallization, we are going to perform a liquid-liquid separation to separate our glycine and our octanoic acid. So we're going to start by putting our mixture of those 2 into a separatory funnel. And you may be thinking, what exactly is a liquid-liquid separation? It's pretty much exactly what it sounds like. It's just you have a mixture of 2 liquids and you want them to be separated. So earlier we were talking about washing and extraction. Those are actually 2 forms of liquid separation. So in this scenario right now, we are going to start with our extracting solvent, which will be diethyl ether. I have it drawn right here going into our separatory funnel with our mixture. Now that is going to help extract the 2, but ideally we want one to be in an aqueous solution and one to be in an organic layer, but both of our compounds are polar. So in this scenario, we're going to add a base, NaOH, and we hope that that will react with the octanoic acid layer. So ideally, the proton will be removed from the OH group on octanoic acid, and that will render the molecule as ionic, which will increase the polarity of it because it now has an ionic charge on it. So glycine is actually a lot denser than octanoic acid, as I have shown here, so we do expect to see it on the bottom layer of the 2. So once it's on the bottom, all separated, we can drain it out of there. Then we're left with our orange solution drawn on top, but we're going to want to make sure that we have all of the glycine removed, so we add more NaOH to it, mix it around, drain it again. After we have our glycine isolated in a flask, we can wash it with a brine solution that will get rid of any excess water so that it isn't contaminated. And after that, we can add drying agent to it. For example, let's say calcium sulfite, because it's neutral and fast acting, so that should roll around freely. If it doesn't, then you've got to add more into there. And then after that, we're going to decant it. So basically what that is filtering it out. So you have a Erlenmeyer flask, you have your filter paper on top, and then you simply just pour it through there to make sure all the chunks are left behind and we're just left with a liquid. After we decant it, we're going to bring it to our rotary evaporator.